Okay, we've been working with functions time and again, and we will continue to do so for the rest of the course. And we have for the first part in the test 2 review, okay, we have a given function f of x is equal to the square root of x plus 11, and we have 3 parts here, and the first 2 of which we have looking for functional values, and then we have the third part we are configuring what the domain is going to be. Okay, so we have for the first item, okay, so we have the given function. Again, we have f of x is equal to the square root of x plus 11, okay, and so for what we have here, so in the first item, again, so you have f of x equal to the square root of x plus 11. And we're looking, first of all, for f of 25. Okay. And again, so again, f of x is a functional notation for what we say is y. Okay, and here we have f of 25. And filling in 25 for the input variable x. So we have the square root of 25 plus 11. And 25 plus 11 is 36. And 36 is a perfect square number. And we have that the square root of 36 is equal to 6. And for what we have in the case of the second part, okay, we're now looking for f of negative 7. Okay. And for this one, okay, for f of negative 7, and working with this value just as we did with 25. So we have the square root of negative 7 plus the 11, and for the sum within the radical we had the square root of 4, and the square root of 4 only reduces to 2. And in the case of the domain, okay, for the given function, again we have f of x is equal to the square root of x plus 11. And because we have a radical that is of an even root, okay, we have the x plus 11 cannot be negative. Okay, now it can be zeroed and it can be positive. Okay, so we have x plus 11 is greater than or equal to 0, so we have the x is greater than or equal to negative 11. Okay, and looking for the interval, again, just taking what we have, looking at it visually. Okay, so you have your focus on the number negative 11, so you have that x is greater than or equal to negative 11. Okay, and so where the equal sign negative 11 is included. And again, for the rest of the values, okay, they will be greater than negative 11. So we're going to have a ray going out to the right, okay, in graphing. And we have continuity, okay, to where we have x to be approaching infinity. Okay, and so it's going to turn out that for the domain of this function, we'll have going from and including negative 11. So this is going to be bracketed, and we have going continuously out to infinity. Okay, so you have, again, just for the results here. Okay, so you have for f of 25, again, that is going to be at 6. F of negative 7 is equal to 2. And for the domain of the function, again, we have going from and including negative 11 out to infinity. Now, for what we have in the next function. Okay, so we have a blend of radical and irrational statement. Okay, and we have for f of x. Okay, we have x minus 3 over the square root of x minus 4. Okay, and just looking at the functional values. Okay, so we're looking at f of 5 and f of 9. So we have for f of 5. Okay, so just plugging in 5 for x. Okay, so we have 5 minus 3 all over the square root of 5 minus 4. And we have 5 minus 3 is 2. We have over the square root of 1. And the square root of 1 is only 1. And so we have a 2 to 1 ratio. So whenever x is 5, your corresponding y value comes out to 2. And for what we have in the case of part B, so we have f of 9. And just plugging in. Now we can put in either two versions of the result. So here we have with x minus 3, we have 9 minus 3. And we have over the square root of 9 minus 4. Okay, so you have 9 minus 3 is 6. 9 minus 4 is 5. Okay, now one version of the answer you can just leave as 6 over the square root of 5. But I do know that probably, depending upon what part of the course, something like trigonometry, you could sort of rewrite this, getting rid of the radical in the denominator. And what you would do here is that you could multiply by 1 in the form of the radical denominator over itself. So we will have 6 times the square root of 5. And the square root of 5 times itself, okay, this would be square root of 25, which is going to go to 5. Okay, so you could utilize either notation. Okay, now for what we have in the case of the domain, right, so to keep f of x as an expression that is defined in the real number system. Okay, now the burden is going to lie with x minus 4. And we have this term as part of an even root radical, and also it is in the denominator position. Okay, and because we have a square root, okay, x minus 4 cannot be negative. And because it is in the denominator, x minus 4 cannot be 0. So this signals that x minus 4 has to be positive. And so for what we have in inequality terms, now we have x minus 4 is greater than 0. And so we'll have that x is greater than 4. And it's by then you can go ahead and write the result for the domain in interval terms. So again, we have the value of interest at 4. Now 4 is not included. For everything in x is going to be greater than this value. So in terms of graphing, we have a ray that will go continuously to the right and approaching infinity. Now, for the domain, we had the exclusive use of parentheses. Okay, so you'll have those around both 4 and infinity. All right. Okay, so for what we have in the setup, okay, so we have, again, we have for f of 5, again, that is at 2, and for f of 9, okay, again, you can say we have 6 over the square root of 5, or 6 times, okay, the square root of 5 over 5, and for the domain of f of x, okay, in interval notation, again, we have parentheses around both 4 and infinity. All right. Now, when we made the transition momentarily from functions and their domain to their values, we had crossed over to equations, and in the case of equations, crossing over into the xy coordinate system, we had like relations among lines, especially those that run parallel and perpendicular. And for what we have in numbers 3 and 4, we're looking at a parallel and perpendicular line to determine. Okay, and we have for the setup here, it says to determine the equation of slope-intercept form of the line with the following characteristics. Okay, and first of all, we have parallel to 2x plus y is equal to 4, and that's going to pass through 3, 3. Okay, so we have for this item, okay, so we have for the given line, okay, again, we have 2x plus y is equal to 4. And we're going to find out, okay, just what the parallel line is going to be. Again, parallel lines are going to have the same slope. Now, in configuring the slope, I'll be looking at putting the equation of this line in slope-intercept form. Okay, so to get it in the form of y is equal to mx plus b. Okay, so if I isolate the y term, so we have taking 2x away from both sides, so we have that y is equal to negative 2x plus 4. Okay, and so we have from this, okay, I have y by itself, and the coefficient that is next to x, okay, that is going to be the slope. So the slope m is equal to negative 2, and the slope of the parallel line is also going to be the same. So for the parallel line, we have the slope m equal to negative 2, and the point through which the parallel line is going to pass, okay, that will be 3, 3. Now, we're going to be looking for the slope-intercept equation of this line, but using the point-slope formula. So you have y minus y of 1 is equal to the slope m times the quantity of x minus x of 1. Okay, so just sort of mapping what we have here. So you have m is at negative 2, and again we have y minus y1, so your y of 1, okay, that is at 3. And the first coordinate will be in reference to x of 1. So just filling in what we have now. Okay, so you have y minus 3 is equal to negative 2 times the quantity of x minus 3. And we have we're distributing negative 2 over the quantity of x minus 3. Okay, so we have negative 2x plus 6. And then finally getting the y term by itself. And then we have upon adding 3. So we're going to have that y is equal to negative 2x plus 9. Okay, so this line is going to have the same slope, again at negative 2. And to test out whether it passes through 3, 3. So if y is at 3, the left-hand side of the equation is 3. And I want the right-hand side of the equation to be 3 as well. So we have an x at 3. Negative 2 times 3 is negative 6. Negative 6 plus 9 comes out to 3. Okay, and so we have for this outcome, again, so for the parallel line, again, we have y is equal to negative 2x plus 3. Okay, now for the next item, okay, we're looking for the equation of the line in slope-intercept form, where it is going to run perpendicular to the line represented by 2x minus y equals 4, and where the perpendicular is going to pass through 2, 7. Okay, so have a little bit of a change up for the given line. And we have, in the case of item 4, okay, so you have 2x minus y is equal to 4. And again, we have, in the case of what we're trying to find, okay, again, it's going to be the line that runs perpendicular to this. Okay. All right, so in determining the slope of the given line, okay, so again, I'm going to put what I have here in terms of the slope-intercept form. So getting the y term by itself. Okay. And so we have taking 2x away from both sides. So I have that negative y is equal to negative 2x plus 4. And then changing over the left-hand side from negative y to positive y. So I can either multiply or divide all the terms out by negative 1. Okay, so we have left-hand side of the equation. Okay, so we have y, and so we have, in this case, so it's negative 1 times negative 2x plus 4. So we have the y is equal to 2x minus 4. So I'm making the negative terms positive and vice versa. So we have for y is equal to 2x minus 4. So we have that the slope m is equal to 2. And just taking what we have with a perpendicular line. Okay. And again, for perpendicular lines, okay, their slope values will have opposite sign reciprocal relations. And so for the given line, the slope is at positive 2. And if I go with an opposite sign reciprocal, I have the slope for the perpendicular is going to be minus 1/2. And again, just sort of as a reminder, again, the product of the slopes of perpendicular lines will be negative 1. Okay, so think of like you got 2 times negative 1/2. And again, the product of the slope values we have at minus 1. And for the perpendicular line, so you have the slope at negative 1/2. And the point through which the perpendicular line passes, okay, that is going to be at 2, 7. And for what we have in the determination of the slope-intercept equation, so in using the point slope formula as the backdrop. Okay, so we have in the setup, okay, so we have slope is at -1/2, and again for x01 and y01, okay, so your x01, okay, we have at 2, and again we have just for 7 is going to be in reference to y of 1. So we have in the setup, so we have y minus 7, and we have is equal to -1/2, and we have times the quantity of x minus 2. We have y minus 7, and we have with the distribution of -1/2 over the quantity of x minus 2. We have -1/2 x plus 1. And we have upon adding 7 to both sides. And so we're going to have here that y is equal to -1/2 of x plus 8. All right, and you can go back and check. All right, so the slopes of 2 and -1/2, those are opposite sign reciprocals, and to see if 2, 7 belongs to this particular equation, so y is at 7, left hand side of the equation is at 7, I want the right hand side to be as well. So we have an x at 2, -1/2 times 2 is -1, and -1 plus 8 is also at 7, so we do have consistency. Alright, so in the case of the perpendicular line, so for the slope-intercept equation, again we have y is equal to -1/2 of x plus 8. Alright, now for what we have in the case of numbers 5 and 6, okay, it says to determine the domain of the following. Okay, so for number 5, okay, we have rational expression. Okay, so you have 2x plus 7 all over x squared plus 4x plus 3. And in this one, okay, so there's going to be a restriction, okay, and again the restriction is going to be that the denominator cannot be at 0. Okay, and so let's go ahead and work here. So we have x squared plus 4x plus 3 cannot be 0. So you have that x plus 3 times x plus 1 cannot be 0. And it's going to follow that for what we have here. So x plus 3 cannot be 0. Then we have the x plus 1 cannot be 0. So we have the x cannot be -3. And we have the x cannot be -1. Okay, so just looking at what we have in the exclusions. Okay, so the excluded values, we have at -3 and -1. Okay, so the graph is going to have holes at those locations. All right, and so for what we have in terms of the domain, okay, so you have two values left out. And what's going to happen, okay, is that for what we have in number 5, if we express in terms of an interval notation, okay, so we have going from negative infinity to negative 3. Okay, and we take in union, okay, with those values between negative 3 and negative 1, and then we'll have those values that will be greater than negative 1. So, and just taking what we have, okay, so have those values of x less than negative 3, and then we have those values of x greater than negative 3 and less than negative 1. And then we will have, for the rest, we have those values of x that will be greater than negative 1. Okay, and that will be the outcome for what we have in the case of number 5. All right, and in the case of what we have for number 6, okay, we have another rational expression. Let me see if I can. Okay. So for number 6, okay, we have f of x is equal to 2x minus 1 all over x squared minus 4. And for what we have here, again, a little history is going to repeat. Again, we have another rational expression, and we have that the denominator cannot be 0. So we have x squared minus 4 cannot be 0. Again, looking at factoring. So you have the quantity of x plus 2 times that of x minus 2 cannot be equal to 0. So we have with x plus 2, okay, we'll have negative 2 excluded. And with x minus 2, we have positive 2 excluded. So we'll have the exclusion of additive inverse of values. And we have with negative and positive 2 left out. Okay, so you have 2 exclusions from the domain, and the interval notation is going to consist of 3 subinterval sections. And so for what we have in 6, we have with the domain, we have starting from the lower end, okay, we have going from negative infinity, approaching negative 2, and then we have going past negative 2, and approaching but not including 2, and having bypassed 2. Okay, we have for the rest of the set, we have those values of x which will be greater than 2. So kind of like what we have in number 5, number 6 is going to have the domain to consist of 3 subinterval sections. Now, for what we have in the next portion, okay, so we're looking at determining, okay, the slope-intercept equation of a line that's going to pass through 2 specified points. And for what we have in this particular item. Okay, so you're looking at the slope and the slope-intercept equation of the line that's going to run through these two ordered pairs. Okay, and so for what we have here, let me go ahead and just write out for 5. So again, the domain. Okay. Okay, so for 7, okay, we're looking for the slope and the slope-intercept equation. So we've got our ordered pairs at -1, -3, as well as 3, 5. And for the case in the determination of the slope, again, we're looking at change in y with respect to change in x. And in the case of operating along the lines of y2 minus y1 all over x2 minus x1, okay, before we try to do anything with that subtracting, we want to go ahead and identify what will be our first and second sets of x and y values. Now remember, x comes before y. Okay, so with -1, -3, since that is mentioned first, we'll have this as the first set. And with 3, 5 given subsequently, we'll have this as the second set. So for the slope itself, okay, so designating what I have for the first and second set of x and y values. We say for y2 minus y1, we have 5 minus -3. And for x minus x2 minus x1, say x2 is going to be at 3. And we have minus x1, so we have minus -1. And again, subtraction of a negative reverts to addition of the positive. So you have 5 plus 3 is 8. 3 plus 1 is 4. And 8/4 is equal to 2. So that is going to be the slope. Now we got the slope, and you can choose either of these ordered pairs in creating the point slope backdrop to the overall determination of the slope-intercept equation. Even though I had -1, -3 for x1, y1, that was just for configuring the slope. Okay, and you could choose -1, -3 since we did work this out as x1, y1 for the slope. But again, you could also choose 3, 5. And for the point slope setup on this one, okay, we have for y minus y01 is equal to the slope m times the quantity of x minus x01. Okay, so for the main portions, okay, so we got slope is at 2. And we got 3 for x01 and 5 for y01. So here we have y minus 5. And we have is equal to the slope m, which is at 2. And we have times the quantity of x minus 3. And we have in the follow through. And upon distributing, so I have y minus 5 is equal to 2x minus 6. And for getting y by itself, And we have upon adding 5 to both sides, so we have that y is equal to 2x minus 1. And you can go back and check, okay, for both of these order pairs. So if y is at 5 and x is 3, you want both sides of the equation to equal. So you got 5. 2 times 3 is 6 minus 1 is also at 5. And to see if this works for -1, -3. So with y at -3, we got x at -1. So we have 2 times -1 is -2. -2 minus 1 is -3. And we have -3 is equal to -3. So this equation does check out for both points. Okay. All right. So just for what we have for number 7. Okay, so we have the slope is equal to 2. And again, for the slope-intercept equation, okay, again, we have y is equal to 2x minus 1. Okay. Now, we have in the determination of functional values and expressions, okay, so we're going to have for item number 8. Again, so we have f of x is equal to -x squared minus x plus 4. Okay. And for the first item, okay, we're looking at f of 3. Okay, now we're looking for the functional value whenever x is at 3. Okay, notice we have the negative of x squared, and you would read this as -1 times the square of the input. Not the square of negative x, but -1 times the square of x. So here, if I fill in 3 for x, so I'm looking at the negative of the square of 3. Not the square of -3, but the negative of 3 squared. And we have minus x, which would be minus 3. And we have followed by the addition of 4. Okay, and so we have negative, and we have 3 squared is going to be 9. And again, we have minus 3 plus 4. And so we have -9 minus 3 is -12. And we have in turn, okay, -12 plus 4 is equal to -8. Now, for the next value, this one's a little bit tricky as well. For f of -2, okay, now I'm looking at the negative of the square of -2, and have minus -2, followed by the addition of 4. All right, and now I'm going to have initially, now for the square of -2, that part is 4, but I still had the distribution of -1 to look at. So this will come out to the negative of 4. Subtraction of -2, that translates out to the addition of 2. And we have plus 4. And working from left to right, or you could have negative and positive 4 to cancel, still come out to 2. But we have -4 plus 2 is -2. -2 plus 4 is equal to positive 2. So we have the f of -2 is equal to 2. Now for our binomial input, and this time we have with f of x plus 4. All right, so now again, so working in line with the function f of the input, you have the negative of the square of the input. So here we have the negative of the square of x plus 4. Then I have subtraction of the input. So I'm going to be looking at the subtraction of all of x plus 4. Again, we have followed by the addition of 4. Okay. And for what we have, again, so I got the negative. Okay, now if I go ahead and square out x plus 4, or x plus 4 times itself, so we have x squared plus 8x plus 16. Okay, so I've squared out the binomial, but I'm still going to multiply those terms out by -1. Now for distributing subtraction over x plus 4, so we'll have -x and a -4. Then we have plus 4 at the end. And so for the negative of the square of x plus 4, so we have -x squared. Then we have minus 8x minus 16 minus x. Okay, and it's by then you could go ahead and cancel out the negative and positive 4. Okay, so once we combine like terms together, so we have -x squared, and then we have -8x and -x, so this will be a -9x. And then we have for the combination of the constants, okay, this will end up at minus 16. Okay, so for this output we have -x squared minus 9x minus 16. All right, and so again for f of 3, again this was at -8, and for f of -2, okay, f of -2 is equal to 2. And for f of x plus 4, again, that output was -x squared minus 9x minus 16. All right. And now, just once again, looking into what we have with piecewise defined functions. And we have, okay, so for number 9, we have our function f of x partitioned into 3 categories. Okay, and so for what we have here, in number 9, okay, so you have for f of x, in this particular case, all right, so we have got -3, absolute value of x, and 7. So this is going to be equal to -3 for those values of x. That will be less than 4. And f of x is going to be equal to the absolute value of x for those values of x whereupon 4 is less than or equal to x, which in turn is going to be less than 8, and we have the f of x is equal to 7 for those values of x that will be greater than or equal to 8. All right. So we have for the parts here, okay, so if we're looking for f of -4 and f of 1/2, as well as f of 6, and also f of 15. Okay, so looking at the inputs now, for -4, -4 is an input that is less than 4. For 1/2, like -4, 1/2 is also less than 4. And for 6, now 6 is not less than 4, but it does lie between 4 and 8. And for 15, okay, 15 is an input that is greater than 8. Okay, so the first inequality applies to the first two items. So for f of -4, okay, as well as f of 1/2, okay, that is automatically set up where y is equal to -3. And since 6 lies between 4 and 8, and since 6 fits into the second inequality description, we're going to have the second functional description to follow. So you have f of the input is equal to the absolute value of the input. So here we're going to have the absolute value of 6, which is equal to 6. And as for f of 15, okay, 15 is greater than or equal to 8, so the last inequality applies. And so the last part of the function feature is going to apply where we have that f of x, if x is greater than or equal to 8, comes out to 7. Okay, so those will be our respective values in this case. Okay, so again we have for f of -4, okay, so that's going to be -3, f of 1/2 is -3, f of 6 is 6, and f of 15 comes out to 7. Okay, and we have in the case of number 10, okay, so we have with again for the 3 separate categories, and we have for this item okay, so we have for f of x, okay, so you have equal to 4x minus 3. For those values of x, okay, they'll be less than 0. Then we have f of x is equal to x squared minus 1. For those values of x such that 0 is less than or equal to x is less than 5. And then we have, once again, for the values greater than or equal to 5, we're going to have that f of x is equal to 2x plus 1. Alright, so we have with the various inputs, okay, so we have f of -3, f of 0.6, we have f of 4.9, and we have f of 5. Okay. And in identifying which part of the function we're going to use for the respective inputs. Okay, so for -3, okay, -3 belongs to the first inequality, so we have -3 is less than 0, so this will belong to the x is less than 0 category, and the corresponding functional part is going to be with 4x minus 3. So we have 4 times -3 minus 3. 4 times -3 is -12. And -12 minus 3, this will come out to minus 15. Now for 0.6, okay, 0.6 cannot be less than 0, but 0.6 does fall between 0 and 5. So here we'll have that 0 is less than or equal to 0.6, which is less than 5. And since this belongs to the second inequality description, we're going to use the second functional characteristic. In this case, you have the square of the input minus 1. So we have 0.6 squared. Okay, so you have 0.36. And if we take away 1, okay, we're going to have a negative value in this case, which will be at minus 0.64. And for 4.9, okay, now there's a vast difference between 4.9 and 0.6 for the input, but 4.9, like 0.6, also belongs in the second category because it also falls between 0 and 5. And again, we're going to use the second functional part. So here we're going to have 4.9 squared minus 1, and the square of 4.9, or 4.9 times itself. Okay, so that's going to be 24.01 minus 1. So we have for the output, this will come out to 23.01. And for what we have in the case of f of 5, okay, 5 cannot be less than itself, and it cannot be greater than itself, but it is equal. And we have the equal sign concerning 5 in the last inequality. So we'll be using the last part of the function for that size input. So utilizing 2x plus 1. So we have 2 times 5 plus 1. And we have 2 times 5 is 10. 10 plus 1 comes out to 11. And so for what we have for these items, okay, in number 10, okay, so you have f of negative 3. So again, that was negative 15. F of 0.6, that was minus 0.64. F of 4.9, have it 23.01. And for f of 5, okay, that came out to 11. All right. Now, looking at what we have concerning functions and their domain. Okay, so you have two functions, f of x and g of x. Now, both of these are going to be linear functions. And for what we have in the setup, okay, so we have f of x is equal to 2x minus 12. And g of x, okay, g of x we have equal to x plus 14. Okay. Now, just looking at what we have for the operational functions. Okay, so we have with number 11, okay, so we're looking at the sum function where we have f plus g of x. And again, just in the expanded notation, so this means we have the sum of f of x and g of x. So again, so for f of x, we have 2x minus 12. And for g of x, okay, so you have x plus 14. And looking at combining, okay, so you have 2x minus 12. Plus x plus 14. And gathering like terms together, so you have 2x plus x, so this will make 3x. Negative 12 plus 14, so that's going to make plus 2. So for the sum of f of x and g of x, okay, so we have 3x plus 2, and we'll get into the domain shortly. Now for the difference, where we have f minus g of x, so we have f of x minus g of x. Okay, so you have 2x minus 12 subtracting all of x plus 14. All right. And so we have in the follow through, so you have 2x minus 12. And now for x plus 14, since that combination is going to be taken away. We'll have subtraction of x as well as that of 14. Here we have 2x minus x becomes x. Negative 12 minus 14, we have it minus 26. And for what we have in the case of the product function, okay, so we have f of x, or f times g of x. So we have f of x times g of x. So we're looking at taking the product of 2x minus 12 and x plus 14, and we have with the distributing. Okay, so you have 2x squared, and you're going to have plus 28x, and you have minus 12x. So 28x minus 12x, that's going to leave us with 16x. And the last product, okay, we have a highly negative value, so that's going to be minus 168. Okay, now, again, the sum, difference, and product functions, they're all going to have the same domain. Okay, and now again, the domain of the sum, difference, and product functions will be on the basis of the combined restrictions from the immediate functions involved. Now for f of x and g of x, okay, these have no restrictions. And g of x, again, has no restrictions. So that means that the sum, difference, and product functions will have no restrictions either. And where there are no restrictions, that means that the domain will be the set of all real numbers. And this will apply to the sum, difference, and the product functions. And again, the quotient function, okay, because we do not have the allowance of a zero-value denominator, okay, there is that possibility that the quotient function can have a domain that is distinct from the other operations. And so for what we have in the case of f over g of x, okay, so you have f of x over g of x. And just specifying, so f of x, okay, we have a 2x minus 12. And g of x, okay, we have an x plus 14. Okay, and this ratio, just filling in for both f of x and g of x, okay, that's going to be in simplest form. Now where the domain is concerned, okay, no longer do we have no restrictions, because here we have g of x cannot be 0. So yeah, the x plus 14 cannot be 0. So we have the x cannot be equal to negative 14. So negative 14 is left out. which we have everything else from the real number system to make up the domain. And so it's going to follow that for the quotient function, the domain will be, again, a combination of those values of x less than negative 14 along with those values of x that will be greater than negative 14. And that will be the result in the domain for the quotient function. Now, and what we have regarding the composition of functions, and we have concerning numbers 15 and 16. And in a sense, okay, we'll be hitting a reset button. Because where the domain is concerned, you're looking at the composition sort of dancing to the beat of another drum. And for, again, so we still have working with f of x. So we still have it 2x minus 12. And g of x. Okay, so we still have it x plus 14. Okay, now in the case of what we have with the compositions, so we have in the case of f composed with g of x. And just writing in sort of the compact notation. So we're now looking at f of g of x. And again, the outside function is f, and the follow-through is going to be in accordance with what we have assigned for f. So here we have f of the input is equal to 2 times the input minus 12. Now we will have with the input at g of x, we have in the initial follow-through. So we have 2 times g of x minus 12. And then going ahead and filling in the variable expression representing g of x, I'm going to be looking at 2 times all of x plus 14 minus 12. And we have with the distributing. So you have 2x plus 28 minus 12. And the resulting composition is going to be at 2x plus 16. Okay. So that'll be the final output here. And again, where the domains, or say the restrictions, okay, for the input and output are concerned. So we have with the input function, again, that was g of x. G of x is equal to x plus 14, and since this is a direct expression, and since we don't have anything like an even root radical, like a square root or a fraction, and because g of x is a linear function, there are no restrictions on this one. And we have for the resulting output, again, that is at 2x plus 16, so you don't have a fraction or an even root radical, so this one has no restrictions. And so since the input function and the overall composition do not have any restrictions between them. That means that for the composition itself, there is no restriction at all. So for the composition whereupon we have f composed with g of x, we have for that domain, then we have the set of all real numbers. And for what we have in the case of the other composition, whereupon we have g composed with f of x. Okay, so you have g of f of x. Now we have the outside function labeled at g, okay, and again operating in accordance with g. So again we have g of the input is equal to the input plus 14. Okay, now for g of f of x, okay, we have the input is f of x. So g of f of x will be f of x plus 14, and then putting in the variable expression that defines f of x. So we have 2x minus 12, followed by the addition of 14. So 2x minus 12 plus 14, and we have for this output, then we have 2x, and negative 12 plus 14 comes out to positive 2. Okay. Alright, so the result here we have it 2x plus 2, and just for the determination of the domain, okay, so we now have the input is f of x. Is equal to 2x minus 12, and since we have just a linear expression, again no fraction, no even root radical, okay, we have no restriction. And while we have a different composition, we still have a result that is free of restrictions. So 2x plus 2, again, for the same reason as the input, there are no restrictions. So you have no restrictions at all. Okay, and just like what we have with the composition in number 15, when we have the domain for the composition in number 16 is still going to be the set of all real numbers. All right. Now, in the case of what we have in the sets, okay, and what I'm going to do for number 17 in this one, okay, I'm going to look into for right now, I'm just going to look into the domain of the first 4 parts. Now we have, you're not looking for the results from taking the operations between the given functions, but you're just looking what we have in the domain. Okay, right now we have f of x equal to 3 over x minus 1, and g of x equal to x over x plus 12. Now for the domains. Okay, so again we have with f of x, again that is 3 over x minus 1. and g of x. See, that was x over x plus 12. Okay, so just look into these first 4 parts. Okay, so we have just for the individual functions, okay, for f of x and g of x. Okay, now for f of x to be defined, we cannot have the 0 denominator. Okay, so x minus 1 cannot be 0. So to be able to work with f of x, okay, x cannot be equal to 1. And for g of x, we have x plus 12 as the denominator. And to be able to work with g of x, x plus 12 cannot be 0, so we have the x cannot be negative 12. Okay. Now for the sum, the difference, and the product functions. Again, we're going to be looking at combining the restrictions. Okay, now the sum, difference, and product functions, again, we have the exact same domain, and the domain is formed by considering the restrictions applied for the individual functions involved. Okay, so to be able to work with for f, x cannot be equal to 1, and to be able to work with g, x cannot be equal to negative 12. So we have just taking what we have in the overall picture. Okay, so we're leaving out both negative 12 and 1. So you have a hole at negative 12 and a hole at 1. Okay, so we have regarding the limits. And it's going to, okay, for the sum, difference, and product functions, it's going to result that for the domain, you have those values of x less than negative 12, along with those values of x, okay, between but not including negative 12 and 1. And then for the rest, you have those values of x that will be greater than 1. Okay. And again, so we have the sum, difference, and product functions. Again, are going to have the exact same domain. And as that results, now for the quotient function, again, that can be the sort of the odd man out in terms of having its domain carried out. So we have for f over g of x, then we have f of x over g of x. Again, f of x, you have 3 over x minus 1. And for g of x, now we have x over x plus 12. Okay. And in terms of the follow-through, so right now I have a ratio between fractions. Okay, and to get out of the fraction of fractions, what I can do here, okay, so you have 3 over x minus 1 divided by x over x plus 12, and we have to undo the division by a fraction. Again, I can multiply by the reciprocal of the fraction on the bottom. So here we have 3 over x minus 1 times x plus 12 over x. So for the resulting quotient function, okay, we have 3 times the quantity of x plus 12. And this will be all over x minus 1 times x, or x times the quantity of x minus 1. Okay, now in terms of the restrictions, now again, to keep I'm still working with both f of x and g of x. So I still have from this part that x cannot be equal to 1, because I still have a fraction with f of x. So I cannot have a 0 denominator for 3 over x minus 1. Likewise, for x over x plus 12, I cannot have a 0 denominator. So I still have the same restriction for g of x. But now, having flipped this bottom fraction, we now have what was the numerator in x from g of x. Now it is flipped over to where it is now on the bottom. So we now have left out 0. Okay, so you had the restrictions for the quotient function from f of x and g of x, and then you have that tertiary restriction from having taken the reciprocal of the denominator fraction, where we now have 0 also excluded. And so we have with the values. Exclude, so we have negative 12 and 0 and 1. Okay, so you have 3 exclusions, and so we're going to have for the interval notation in defining the domain. Okay, this will be a little bit of a longer statement. All right, so just taking what we have now. Okay, so for the domain of the quotient function, okay, so you have those values less than negative 12. And then we have those values of x between negative 12 and 0. And then we have in the next, okay, we have those values between 0 and 1, but not including 0 or 1. And we have rounding out the rest. You're going to have those values of x, okay, that will be greater than 1. Okay. And so, while the sum, difference, and product functions have the domain to be these 3 sections, it is with the added restriction leaving 0 out, that the interval notation for the domain of the quotient function turns out to have this particular added subset in the mix. Okay. And we will look into the compositions, but tell you what, if we go ahead and look into the second part here. Okay, and just for those domains, okay, so we have in the first item, okay, so we have x minus 1 all over x squared minus 4x plus 3. And okay, now just looking for the domain, okay, for this one. And the reason I had a function like this set up is that it is easy to think that, okay, if you notice, if I were to factor, I would have like x minus 1 times x minus 3, and some might make the careless mistake of canceling out like factors between the numerator and denominator, saying that there's going to be only one restriction. And let me mention, okay, so never cancel factors. In determining domain. Only time you would cancel factors, like in terms of any significance of canceling other than just reduction itself, this would be like determining, and this is a future topic, and this would be what would be regarded as vertical asymptotes. In other words, those would be vertical boundaries that would split the graph of a rational function. So I just wanted to go ahead and mention this. So just kind of hitting the reset button. Okay, so you have, given the function, have f of x equal to x minus 1 all over x squared minus 4x plus 3. So again, we have with the restriction, okay, the denominator, and we're looking at the original form of the denominator, cannot be equal to 0. So for x squared minus 4x plus 3, then we're going to have with our trinomial disallow from equaling 0. Same thing is going to apply to the factors. And for the factors, I have x minus 1 and x minus 3. Again, those cannot be equal to 0. And if x minus 1 cannot be 0, okay, so you have x cannot be 1. And for x minus 3, if that cannot be 0, well, we have the x cannot be equal to 3 either. Okay, so just for the makeup here, again, the graphing is not required, but again, just to provide a visual representation. And so we're going to have, for the domain, we have two exclusions, so we have three separate partitions in the interval notation. So you'll be looking at those values of x less than 1. So you have parentheses around negative infinity and 1. Then you have those values of x greater than 1 and less than 3. So we still have parentheses. And then for the last, we have those values of x which will be greater than 3. All right. And for what we have in the case of the next function, okay, and so we have 2x squared over x plus 5. Yes. Double check here. G of x, okay. Okay, and just for the restriction on this, okay, so you have x plus 5 cannot be 0, and so we're going to have that negative 5 is going to be left out. So you have a whole on negative 5. Again, we have activity to the left as well as to the right. And so for this rational expression, okay, we're going to have for the domain, okay, have those values of x less than negative 5, along with those values of x that will be greater than negative 5. So again, we have the overall use of parentheses throughout the subintervals that define the domain. Yeah, let's see, now we have h of x, that was the square root of 9 minus 5x. Okay, so we have with this radical function, and it's an even root, and since we have a square root function, now we don't have a fraction, so there is no restriction in terms of 9 minus 5x not being 0. If I had the reciprocal of this statement, you would have that second restriction with not being 0, but here we just have that 9 minus 5x cannot be negative. So it can be 0 or positive. So you have 9 minus 5x is greater than or equal to 0. And we have getting the x term by itself. So if I take 9 away from both sides, so I have negative 5x is greater than or equal to negative 9. Okay, now in the case of getting it down to x, remember, if I'm not add or subtract, but if I multiply or divide by a negative, then the direction of the inequality is going to change. So here we have going from greater than or equal to less than or equal to. And so we're going to have that x is less than or equal to 9/5, or 1.8. Okay, so you have 9/5. Again, that's a fraction that is very close to 2. And for the activity, so you have less than or equal to 9/5, so 9/5 is part of the solution. And we have a ray going continuously out to the left. And you have tending continuously and reaching out to negative infinity. Okay, and so for the domain that we have here, okay, so you have going from negative infinity, approaching and including 9/5, and the 9/5, okay, is going to be in the bracket.